Welcome to Electronic Geek. In this video, we will be dealing with parity generators and we will cover different topics like what is a parity bit, why it is used, and where it is used, different types of parity generators, and we will see its simulation on Tinkercad, and I'll show you the circuit diagram on Proteus. So let's get started. During data transmission, be it wired or wireless, it may so happen that the data you send from the transmitter may not be the exact which is received on the receiving end. So why does this happen? It is because of the noise or some kind of distortion or any other technical factors which lead to changing of bits in the data frame, by which the data sent through the transmitter is not the same at what is received at the receiving end. To ensure that the data sent is same as that received, what we do is we add one more bit to our data frame, which is called as the parity bit. So there are two types of parity bit. One is even parity and the other is odd parity. Now in case of even parity, the parity bit will adjust itself to either 0 or 1, such that the total number of ones in the entire data frame including the parity bit is even number. So if you are having a data frame of let's say a 3-bit data frame of 0 0 1, so right now the total number of ones are 1, and that's an odd number. So what it does is parity bit will be high, that's 1. So now the total number of ones in the entire data frame are even. So that's what is even parity. Now coming to the odd parity. Odd parity is the total number of ones in the entire data frame including the parity bit will be odd. So if you are having a data frame like 0 1 1, so in this case in the data frame right now there are two ones, and which is an even number, so parity bit will be low, that is 0. Now coming to the odd parity. So in case of odd parity, the parity bit will adjust itself to either 0 or 1, such that the total number of ones in the entire data frame including the parity bit are always odd. So let's consider a data frame like 0 1 1. So in this case there are two ones, that is 2 bits are high, and that means that there are even number of ones in the data frame. So for odd parity, the parity bit will change to 1. So now the total number of ones in the entire data frame are odd. So this is odd parity. And coming to the circuit for even parity generator for 3 bits, to start with we will be needing the truth table. So this is the truth table over here. As you can see, these three A, B and C are the data bits, and this is the parity. So you can see 0 0 0, and this is for even. So the total number of ones in the entire data frame should be even. So right now it's 0. If you can see here in this case, second case, it's 0 0 1. So for this, parity is high, and you can check for others this. Coming to the logical expression which is needed for designing the circuit, as you can see, the output, that is the parity bit, is high only when there are odd number of inputs are high. You see, odd number of inputs here, 1 is high, so the output is high. When there are two ones in the circuit, the when there are two ones in the input side, the parity bit is 0. So always remember that when odd number of inputs are high and you are getting the output high for that particular case, the answer is XOR operation of all the bits. So in this case, for even parity generator, the logical expression that I can write is A XOR B XOR C. That's it. It's as simple as that. Coming to the odd parity generator. So you can see here, as there are no ones in the entire data frame, the parity bit is high to make the total number of ones as odd. So you can see when there are even number of ones in the data frame high, so the parity is high. So regarding to the logical expression of 3-bit odd parity generator, we can it's better to go with directly writing this equation rather than going for k map in this case, because you won't be getting any pairs. So if you see here, for this particular expression, it's a bar, b bar, c bar, see all are 0, so expression will be a bar, b bar, c bar. For this case, it will be a bar, b c, see here a bar, b c. For this one it will be a, b bar, c, it's here, and for this one it will be a, b, c bar. So coming to the next point as to how you can reduce this particular circuit, so I will show you as to how to reduce it. So yeah, so this is our equation, and we are supposed to reduce it. In order to reduce it, what you can do is you can basically take a bar common from these two terms and a common from these two terms. So what you will be getting, let's write it. A bar, and in bracket you get b bar, c bar, b bar, c bar plus bc, and when you take a common over here, what you get is b bar c plus bc bar. Okay, and now you can easily identify this particular part. This is b XOR c, this is b XOR c, and this particular part is b XNOR c. Now if you want to know how did I get this, you can simplify this particular bracket using the De Morgan identities. You can write b bar c bar as b plus c the whole bar, and bc as b bar plus c bar the whole bar. Then you will be and you again, if you apply the other identities, you will come to a point where you will get bc bar plus b bar c the whole bar, and that's the same as XNOR operation. So now I can easily write this as a bar in bracket b XNOR c plus a in bracket b XOR c. Now the next thing, I can write this b XNOR c as b XOR c complement. Okay, so if I do that, what will it become? It will be a bar in bracket b XOR c, add and complement it over here like this, plus a into b XOR c. Now if you compare this particular term, this entire, with this thing, it is almost the same thing. Okay, so what it turns out to be, I give this particular term name as alpha, so it becomes a complement alpha complement plus a alpha, and now I can write this as a XNOR alpha, and if I even simplify it, I will be getting a XNOR b XOR c. Okay, so the final thing turns out to be a XNOR b XOR c. So this is the logic equation, and we are supposed to implement this to get our 3-bit odd parity generator. So I will be showing you the circuit diagram on Proteus, and later we will be moving to Tinkercad for its simulation. So let's go to Proteus. Now see, these are the two circuits. Firstly, we will be starting with 3-bit even parity generator. Yeah, so as discussed, the equation for our 3-bit even parity generator was a XOR b XOR c, and as you can see, these two particular switches, I am naming it as a and b, this is c. So the output is a XOR b XOR c. Now let's compare our inputs with the truth table. So our first inputs are 0 0 0, so we will click on start simulation. So right now it is 0 0 0 and you can see the parity bit is low. Check it with this particular parity is 0. Change this particular to 1 and see it's high. This means that total number of bits in data frame are even. So like this you can verify for other inputs too. See, it's low. As there are already two inputs high, the parity is 0. Again for this one it's high to make this all even. So let's stop it and proceed to odd parity generator. So open the truth table and we'll check it. So see, as all these three are low, the output is high, and if I change this to 1, it will be low. See, only 1. Let's even change this. See, as there are 3 odd number of high inputs, the parity is low. So this is the circuit for odd parity generator, and we'll be proceeding to Tinkercad for the circuit simulation. So let's move on to Tinkercad. So here we are on Tinkercad and we will start making the circuit. So we will be needing a breadboard. Place it. Power supply. 1 second. And cancel this. LEDs we will be requiring. In the first one we are making the even parity generator, so and we will be even requiring switches. We'll be using this one, 4-way switch and an XOR gate. So 7486 is the IC number for XOR gate. So okay, we have all the components and let's start making connections. So first of all, every IC, in every most of the ICs there are ground and power pins which you need to connect to the respective plus VCC and ground pin. So supply this over here and change the color to red, as this is the power line, and this to black. Supply this particular ground line to here also. We will be needing it to ground the IC, and for the LED also connect this ground pin over here, change the color, and the power pin to plus VCC. So connect all these pins to plus VCC like this, the ones that we will be using, and a resistor over here which will limit the current, and change this value to 510 ohms. It's pretty fine. And yeah, so connect these pins. The expression that we needed was A XOR B XOR C. So connect all these pins over here. This is first input, this one is the second one, like this. Output of these will will be fed as an input to the other gate, and the third one, like this. And this output shall be fed to an input over here, and this particular pin, which is the cathode pin, shall be grounded. Change the color to black just for avoiding confusions. So let's start the simulation. As per our first expectation, when all the three inputs are 0, the output also shall be 0. So see, when all are 0, the parity bit, which is this LED, is 0. Change this one. See, it's high in order to make the total number of ones even. Again it's 0, and again it should be high. Yeah, it is. So our circuit is working fine. So we are done with the even parity generator, and now we will be doing the odd parity generator. So stop this and modification of this circuit a little bit. also remove these two wires. Now what we will be needing is the NOT gate also. So this is the NOT gate over here. Do the similar things that were done over here. Connect the power pin to plus VCC, sorry, escape, like this, and the ground to the ground pin. Okay, so the expression needed is A XNOR B XOR C. Okay, so assume this as a BC. So this particular output is nothing but B XOR C. So our first term is ready. Now what we need is A XNOR. So unfortunately in Tinkercad we are not having the XNOR, so we are using the NOT gate to achieve the same operation. So this particular output will be given to an input over here, and this A pin will be connected to this one. The output will be fed to the NOT gate like this, and search for the LED. Yeah, like this. Resistor over here, and this output will be fed to the input over here, and connect this to ground. So our circuit is now ready for simulation. This is the odd parity generator circuit, and let's check. So for the case when all of these are high right now, the LED that it should be low. So start it. Yeah, see, it's low because already there are odd number of ones which are high, and change this anyone to low, it will be high. See, it's high. Again change this, it will be off. Change this to high. See, so ultimately in case of an odd parity generator circuit, what we are getting is the total number of ones in the data frame are odd. This is it. Thank you for being till here. Thank you so much. Please do like, share and subscribe my channel, and do let me know your valuable feedback in the comment section. Thank you for being till here. Thank you so much.